So let's start. So today we are going to talk about neural networks, and I will briefly give you an overview what neural networks are and some motivations of why we need them. And after that, in the next lecture, we are going to cover convolutional neural networks, followed by a lecture on how we can train these networks. Okay, so that will be the strategy. So let's begin with neural networks. So in the previous lectures, what we have seen is we have learned how to extract edges from images. And so let's see like how we can make use of those edges. So given an input image, now we know how to compute gradients in the images, how to compute edges in the images. And there are many other low-level processing which we can perform on images, such as we can find key points, and we can also find like many other fine-grained features. So we won't be covering all of those in this lecture because we are going to focus more on the deep learning aspect of computer vision. Now, once we have those kind of low-level features, what we can do is we can use these low-level features to extract image features, which is like a good representation of what we are going to perceive from that particular image. And why we need features? We need features because they are useful for doing like a bunch of different tasks. We can use features for problems such as scene recognition, place recognition, or object recognition. We can use them for detection tasks, and we can also use them for segmentation tasks. Now, let's just, for this lecture, just focus on the classification problem, and we will look into object classification. And by that, I mean is like given an image, we want to recognize what different objects are present in this particular image. Okay, so for that, what we need is we'll have this images input, and then we will have some machine learning component in between, and I will briefly cover what this machine learning component is going to be. So given this images input, we'll have this machine learning framework, which is going to predict what object is present in this image. So for example, if it's a motorcycle, okay? Now, why this problem is hard? So this is a motorbike, and we can easily perceive this, right? And we can recognize it very easily because we are looking at this particular image. But as we discussed like in previous lectures, what a computer or a camera will see is something like this. So this is a patch coming from this particular location in this image. So we just have these bunch of numbers. And using just these numbers, it's pretty hard to recognize like what actually is present in that image. So let's try to figure out why that's the case. So that was our input image. And let's say we are passing this image to a learning algorithm. Now, if we consider or focus on these 2 pixel locations, so what exactly we'll have there? We'll have some bunch of intensity values, and they will be like corresponding to the 3 channels R, G, and B. So let's just focus on like one channel, okay? And let's plot like these pixel intensities in this 2-dimensional coordinate. So this is like for pixel 1, and this is for pixel 2. And let's say if we have the raw image of a motorbike, so for pixel 1, the intensity was like pretty low. And at pixel 2, the intensity was pretty high, okay, this value. Now we have another image of a motorbike, and we will have to consider the same pixel location which we considered for the first image. So in this case, what we observe is like for pixel 1, the intensity was pretty high, but for pixel 2, it was pretty low. So if we plot these 2 points in this coordinate system, the first image of the motorbike we can plot it somewhere here, and the second will be lying somewhere here. Now these are some other random images which are actually from a negative class, and by negative class I means like images which are not motorbikes. So this is like, for example, is an image of a tree, and if we consider the same 2 pixels for this particular image, we can plot the points somewhere at this location. So both pixel 1 and pixel 2 have high intensities, and similarly you can do for this car object, right? Now, if you look at these plot, what we want to do is we want to automatically detect whether a motorbike was present in this particular image or this particular image. So to have such a function which can do that task, and by function I mean like a machine learning algorithm, will have to like draw some kind of boundary in this plane which will easily differentiate between the points which belong to motorbike and negative classes. So in this case, it's fine when we can't draw a linear boundary or a curve, but we can still like draw a circle here and a circle here, and we can say that all the points which are inside these two circles belong to the motorbike class, and which are like outside these circles, they are the negative classes. So now again, these are like just 4 samples. What if we have lot many other samples? So we might have something like this. Now the boundary becomes very complicated. And as you add like more points, it's going to be more complicated. So what's the issue here? The issue is the pixel intensities are not like very discriminative when we compare two different classes or pictures of two different classes. And there are many reasons for that, because the location might change like for one motorbike in one image, and it might be like a flip version of the same motorbike in a different image, but still that's a motorbike, right? So the pixel values will change. So clearly like using pixel values is it's not a good idea for classifying like objects and images. Now what we can do about this? So we can do something better, and that better is like, what if we try to predict like different components of this particular object. So in this case, we have a motorbike. So what we can do is we can try to determine if this particular image has like handlebars, or if this particular image has wheels. So if we can extract features like this, then they will be more meaningful. So then let's say we have such a method which can extract these two kind of features. Then if we try to plot them again on like this 2D coordinate system, so this axis is showing like whether handlebars are present or not. This axis is showing like whether wheels are present or not. So you can see that most of the motorbikes will have handlebars and you will have wheels. So they will lie somewhere here. It's just like the probability you have that might vary. All right. And for all the negative classes, it would lie somewhere here. Okay, then you can easily draw a straight line dividing these two. And that straight line you can represent using a function. It's just a linear equation, right? And you can determine like whether the point falls on the top of that line or below that line. You can easily classify whether that image is motorcycle or not. But the question is how to get like useful features like this. So that's the challenge. Now we have several techniques like to extract such features. For example, we have SIF features. So these were, I think, introduced in 1990s, like 1999 or somewhere around that time. And they are trying to actually, they are based on some key points in your image, and they try to find image gradients at those key point locations. And based on those gradients, you form a feature vector, which is like scale invariant. And we have other features like spin image. So in this case, what we do is, so instead of like a viewpoint, which is like from the point of the viewer, like if you're looking at this image. So if you want to create a representation which is independent of like from which viewpoint you're looking at this image. So for that, what we do is like we can actually have an object oriented viewpoint, which means that irrespective of from which viewpoint you are watching at this object, you will have the same representation. So for that, we have this spin image. Similarly, we have histogram of gradients. Again, these are based on like edges you detect on the images. And this topic, I think we are going to cover in one of the lectures, where we will see like how we can extract image features using this histogram of gradients and use those features for image classification. So similarly, we have lots of other features which you can extract from images. Now, one big limitation is like if you want to extract such features which are useful, you need like some kind of domain knowledge of like that problem. And so these require like, they are very time consuming, and you will have to have this expert knowledge to be able to extract these features. Now, what we do today is, so this was like feature engineering. You have the expert knowledge, you have the like a good idea of that particular domain, the problem you're trying to solve. So you can do some handcrafting of features. You know that which location in the image are important. You will extract features only from that location. So all of that is called feature engineering. So we used to do that before deep learning era, but now what we do is we do feature learning. And we don't care about like any expert knowledge. What we assume is that we'll have the data and we'll perform some kind of learning, and we will uh, study that in detail. So that can be used to learn the features automatically. So we don't need any feature engineering. So we are going to cover both of these aspects, and we will see like how we can use feature engineering to solve different tasks. And then we'll see that how we can automatically learn those features to solve the same problem. And we will see like which one is better. Of course, like feature learning is better than feature engineering. But anyways, we are going to compare these two in all the problems which we are going to study in this course. So as I said earlier, feature engineering, you will have to have expert knowledge, but feature learning, you need lots of data. Okay. Now that being said, let's come back to the problem of image classification. So as I said earlier, for feature learning, you need lots of data. And for image classification, we have such a data set which we call ImageNet. So this data set was, I think, introduced in late 2000s, and it was, I think, it became very popular in 2012 when deep learning was used over this data set. And so the categories of the objects which are in this data set, they're used from WordNet, and they have around 1,000 different categories. So we also call these like 1,000 classes. And I think initially we had around 1 million images, but today we have around 14 million images in this data set. So it's pretty huge. In the test set, we have 100K images, and we'll cover like what test set is, what a training set is. So to learn features or to train your models or to also extract your features before testing, you need some training images, all right? And you use these images to train your classifier. You also have another set which is called a validation set. So this set is used like to, if you have to fine tune any parameters in your network or you have any parameters, so you can use this validation set to improve like your classifier. And then finally you have the testing images which like you can't touch. This will only be provided you for testing to evaluate your model. So there will be secret labels. You can measure like error and all kind of matrices which you want. And there are different variations of this, like how you can use your training data and your validation data. You can have cross validation. You can randomly split like a training data into smaller validation sets multiple times. So, but those details are like from machine learning. So we are not going to talk about those in detail here. So let me see, I think there's a question. So the question is from Brandon, and he's asking, will we always need to use validation images? So in this course, the answer is no. So we won't need any validation set, I think, for most of the problems. Now, this validation set was required when we had classifiers such as SVM. I think you might know if you have taken like any machine learning course. So if you learn your SVM classifier, there are lots of parameters or hyperparameters there which you have to tune based on your current problem or the data set you have in hand. So in those scenarios, validation set actually plays a crucial role. But like when we are training our models in a deep learning scenario, then validation set, like it doesn't play a major role there. So I hope that answers your question. Okay, great. So there is another question from Jeng Tai. He's saying, does the feature engineering and feature learning is the key difference between machine learning and deep learning? So first of all, machine learning and deep learning, I mean, they are not different. Deep learning is part of machine learning, right? So machine learning is a bigger area, and Okay, so he's saying I mean pre-processing. Now I'm confused. So you were talking about feature engineering, which means that you have some data, you want to extract some meaningful features, and then you are comparing that with feature learning, which means that again you will not like handcraft those features, you will try to learn those features. Now I'm confused, like why you brought up like pre-processing. So can you elaborate on that? Probably you can use your mic if you want. That's perfectly fine. We can't hear you. Okay. So did that answer your question? All right. All right. So where were we? Okay. So you have these different splits in your data set. That's fine. Now, so there are two different phases. The first is training phase, where you have the training images. Then what you do is you extract features from these training images, and then you have some kind of system or a function which will map like these features or the input images to some label space depending on the task. So if it's classification, it will map like these images to one of the classes. So this we call like a training system or a framework, or we can also call this as a function. So we have to train that. And to train such a system, we will need some labels. So right now we're just focusing on classification, and we are talking about supervised settings. For that, we need labels. Okay. And once we complete all these three steps, we'll have the trained classifier, which we can actually use during our test time. So during testing, you will have like some images which you have not seen during training. So these will be like unseen images. Then again, you will use the same method which you use for feature extraction in the training phase, in the testing phase as well. And then you will have this trained classifier. You will pass those extracted features to the trained classifier here, and the classifier will make some prediction. So that's like a general idea how you train your network and use that for prediction during test time. Okay, so there is a question from Jan. So he's asking, can a model be trained to identify multiple types of objects at the same time? Now, so when you say multiple types of objects, so do you mean like multiple objects like this? You have apple, you have pear, you have tomato, then you have cow, or you
Oh,
mean like you have all of these objects in the same image?
Um, what I mean is like we have a data set and the images all have labels. So because it sees multiple images with different labels, it learns to identify features that go with each image. Like, is
Mhm.
that a thing that happens?
Yes. So what do you mean by like multiple types of object?
Like in the picture you have, there's animals and then there's fruits. So these fruits and animals are labeled. And
Right.
since the model is seeing all of these images, would it learn to identify the cow and the pear and the apple at the same time since it's seeing all of these images?
No, so your network or your model will see like one image at a time. Okay, so it could be like an image of a cow. So then it will predict there is a cow present. And then you will maybe show like an image of a dog to the same network or the same model. And then it will say like whether a dog is present or not. So what will happen is, so let's say you have these classes. So you have 6 different classes in this particular case, right? So your model will be trained to predict like any of these categories. So there will be like 6 predictions, and each prediction will say like whether this object is present or not. And at a time, like only one image or image of one object will be shown to the model. So is it clear, or because I'm confused like what you're trying to ask?
I think I understand. Since we're only doing one image at a time, it would only be predicting for one class of object.
Right. So yeah, always like your network, your model will see one image at a time. I mean, of course, like in real practice, I mean, you will pass several images, but conceptually, it's looking at like one image at a time.
Thank you, Professor.
Okay. All right. So now let's look at the first component, this image features. So because we need these features during training time as well as during testing time. Now, as we know that these features can be handcrafted features or these can be like learned features. And of course, like we can directly use the pixel values of the image as well. So depending on the task. So if the object is like very complicated, let's say you're doing scene classification, then you might have trouble like recognizing using the pixel values. But if like the image is very trivial, let's say you're trying to recognize digits. So in that case, you can train such a system by merely using the pixel values as well. So we will see that like how that can be done. Okay, so I think we covered this features. These are like handcrafted features. We can also use raw pixel values directly passing in the image. We can have features like histograms. We can use templates, and these are like all the descriptors. And then we can have learn features. Now, the second thing is we need some kind of labels to train this model. And let's see like what these labels are. So these labels like depend on like what kind of task we're trying to solve. If you are doing recognition, let's say image recognition or object recognition, so what you will have is you will have a set of images. Let's say you have a class such as motorbike in your data set and you want to recognize motorbikes. So you'll have lots of these images and you will need labels for these images. So again, it will depend like what kind of task we're trying to solve. If you just want to say that, okay, in this picture, a motorbike is present. So then you will need a label something like this. So for each image, you will have like whether a motorbike is present or not. So that's called like a label, and it's like image label. Then you can be like you can come up with a more sophisticated model, which can not just say that a motorbike is present in this image. It can also say where the motorbike is present in the image. So for that, you can draw a bounding box around this. So then this can be a label to the image. So that's like the second type. You can be more sophisticated. You can say that I exactly want to locate where the motorbike is. So this is, you can draw the boundary around the motorbike. And this is another kind of labels or another kind of annotations you can have. And this is kind of like pixel-wise annotations, because at each pixel, you know like whether there is a motorbike present or not. And there can be like other varieties such as this. You just want to determine like the key points in that image. So for motorbike, it's around this location, around tires, around engine, and the seat. So these are like different variations of annotations you can have, and it depends upon like what kind of problem you're trying to solve. So for the basic problem, image classification, we just need the image and the label saying whether that object is present or not. Okay. So yeah, I mean, depending on the problem, we should have the correct answer, and we call this correct answer a ground truth as well. All right, so if we need labels like on all the images, then we call that supervised learning. And let me try to briefly cover like different kind of learnings we can have. So for example, let's say you are doing semantic segmentation or object detection, right? So, okay, I think there's a question. So Furkan is asking, if we have a cropped image, can deep learning predict the crop part on the image, what is there or what is not, like regression in ML? Okay, cropped image, can deep predict the crop part on the image, what is there or what is not? So let me go back. So what do you mean by cropped image? Do you mean like this just a red rectangle?
Like suppose we don't, you see the trees over there? Like suppose the image is cropped by the trees, so like there are no trees anymore. Can we use this picture still and using the deep learning technique and to apply the deep learning to see what's there actually before the cropping happened? Like, is there really tree over there or not before the cropping happened? Like,
So
can
you're
it?
saying that your network will see like just this red region?
No. Yeah. I mean, I'm not actually talking about the red square, red vision, but I'm just seeing if deep learning can predict what is the outside of the frame, what is there in the outside of the frame. Is that I'm really beginner to this, so I don't know if deep learning can be used such things.
Right. So I think I might have got your question. So what you're trying to say is, let's say you have this image, and we don't care whether cropped or not. So just consider this image, and you are saying that can you have a network or a deep learning network which can say that you have trees at this location? That's what you want?
Yeah.
So yeah, so we call that problem like object detection, or you can also do that using semantic segmentation. So what will happen is that network can predict like you have bike at these pixel locations, and it can also predict like you have road at this location. Then it can predict there are trees at this location. So it depends, like, so there are two flavors. One is object detection, and if during your training you have annotations for like trees as an object, then it will be able to detect these trees. And if you have road as an object, it will be able to detect the road here. And the second variation is semantic segmentation, where each pixel you will tell whether this is a tree, whether this is a bike, this is a road, or this is a sky, right?
Okay.
So yes, you can do that.
Okay, understand. Thank you.
All right. And we're going to cover that in, I think, one of the lecture later in this class. Okay, so there is one more question from Sami. So if we crop out the wheel, could it know that the wheel is missing? So that's like kind of a hard problem. And so let me think like in which category this problem will fall. So for that, you will need like a more detailed semantic information of your object. And that should have like a bike consists of maybe handles, then tank, and two different tires. So I guess, I haven't seen like any such problems yet, but I'm sure like if you have such a data set where you have that detailed level of semantic information about the objects, then you can easily detect like whether all the components of that object represent or not. Okay, so yeah, but definitely this is like a more complex problem than just object detection or classification. So there is a comment from Joel who's saying that that sounds similar to how Face ID can recognize you with glasses on. So with glasses on, that's kind of a different problem. So that will be, I think, face recognition. So similar to image recognition, but then you have different biases or different context information there. So when you wear glasses, then your features might change. So then you need features in such a way that which can ignore like those kind of biases. For example, the glasses or your hairstyle in recognizing faces. Okay. Okay, so let's continue. I think we might get late today. Okay, so fully supervised is if you are solving a problem and you have all the necessary labels or the ground truth which you need to train such a system. So in case of classification, if you're saying that whether an object category is present or not, so you should have that ground truth available to train a system, and that's called fully supervised. So for example, we have a data set called MS-COCO, which is used for different kind of tasks, but there we also have this semantic segmentation. So then we have at each pixel location, we know like which object is present or not. Then a more relaxed setting is weakly supervised. And what happens here is you don't have like all the information you require or you need to solve that problem. So I think a simple category there will be if you want to perform object detection. So object detection means given an image, not only you will identify which objects are present, you will also try to localize where in the image the objects are. Okay, so that's the problem. But during training, we are only given like the image level labels. Like it will only say that this particular object is present or not. We will not have like the bounding boxes or any pixel wise annotations. So that's like partial information available. We call that weakly supervised. Okay, and an example is like if you're using ImageNet for object detection, that's a good example. And the final, the other extreme is unsupervised. So in this case, you don't have any labels at all. Okay, so this is like more labels, this is less labels. Now this is kind of fuzzy and it depends upon like what kind of problem you're solving. And there is another variation which we call semi-supervised. So this is different from weakly supervised. So don't confuse between these two. Semi-supervised is like when you have partial labeling available. So for example, you're trying to solve image classification, all right? And let's say you have 100,000 images in your data set, but only 20,000 of the images have labels available and rest of the 80,000 have like nothing. So that's called semi-supervised. So that's labels. And now let's talk about this training stuff. So what this is. So for training, we need some kind of machine learning framework. And the goal here is given the image features as input, what we want to do is we want to make some predictions. And this can be a function. So let's call this a function f. And let's say you are giving as input the features of this image apple, or it can be this image itself. And what this function have to do is it will have to predict whether apple is present or not. Same for tomato and same for a cow. Okay, so this will be the input, that will be the output, and this is the machine learning framework which we are going to figure out how to train such a thing. So image features, the prediction function, we also call this a classifier if we are doing image classification. And that's the output label. Okay, so the training phase will have a training set, right? Where we'll have labeled examples. And the labeled examples will be something like this. So X1 is image 1, then image n, we'll have n such images, and we'll have corresponding labels. So this Y1 is saying whether apple is present or whether cow is present. So we'll have that label for all the images. And then we will use like this data set to train this network F. And there are different ways. I'm not going into detail right now, but after training that, what will happen is it's going to give you a function. If you apply that function on some unseen test examples, it will predict like the value which you are looking for. Okay. Now, let's see like how we can use neural networks as these functions. So we will replace these functions with just neural networks. And of course, we can have many different variations from machine learning. Now, let's try to cover some background before we go deep. So in our brain, we have these neurons. And this is like a typical structure of a neuron where we have the cell body, which actually is like kind of doing all the processing. Okay. And let's focus on like three more things. The first is dendrite. So these dendrites are like connected to other neurons, similar neurons, and then they take input from those neurons. So there are some signals like passing through this and then reaching this cell body. And then what happens is we'll have inputs through all these dendrites, and then you will perform some operation here using the cell body, and then resultant signal will be passed through this axon, and these are called like synapses here, and these are again connected to other neurons. So then this is going to be like the output and again input to the other neurons. Now there are like lots of neurons in our brain. So this I just explained, like they receive input from other neurons from its synapses, and the operation in the cell body is approximately like summation of all those inputs. And when the like resultant output is like it exceeds some kind of threshold, then that signal is passed through this axon to other neurons. So these neural nets can be biological models like we have in our brain, or these can be artificial models like what we are aiming for. So what we want is we want to develop these artificial systems which are based on these neural nets, and we want them to perform sophisticated computations similar to human brain. So that's the end goal. Now let's do some comparison between brain and a computer. So in brain we have around 200 billion neurons and 32 trillion synapses. So that's a lot. And in a computer, typically we have 1 billion bytes of RAM and trillions of bytes on disk, right? So we are comparing the storage like disk with the synapses and the computer memory RAM with the neurons, because that's where like the processing is happening. So in terms of energy, both are like kind of similar. In terms of processing speed, the computers are like much faster when compared to brain. And this is, I think, is the most important feature of brain, that all the neurons can operate in parallel. And that's not possible in a computer. We do need like a centralized system which controls different threads. So we still don't know how to do that in a parallel fashion. So that's like one big difference. So this is fine. We have fault tolerance in our brain. We have some like fault tolerance to some level in the computers as well. And the other major difference is human brain can learn, but computers, we are not sure. To some extent it can learn. And of course, like usually like human brain, we have intelligence, and for computers, it's a no at this time. So there is a question from Furkan, what does parallel mean in that? So parallel mean they can operate like without interference with each other. They can operate in parallel. So like your brain and my brain, they can operate in parallel, right? So they don't need to interfere with each other. All right. So let's see like how we can implement a simple neuron. So what we have from the dendrites, we have some inputs, right? So these x1, x2, and up to xn, we can consider these as input. So these will be like our input signal. And then we'll have some kind of weights which we will use on these inputs, because different dendrites might have like different strengths. So to simulate that, we'll use these weights, and then we'll add up all these input values. So this is kind of a weighted average, which we I think learned in lecture 2 when we were doing a review of linear algebra. So you will see like how all of that is coming back here. And then whatever output we get, that will be a scalar. So based on like how, based on like the threshold, whether it's clearing the threshold or not, we will generate output here, and which will be passed to like the next neuron. Okay, so this is like a simple replication of actual neuron. So we'll have the dendrites, we have the inputs, we have the cell body, the output will pass to the axon. Okay, so let's see like what actually is happening. So if we have an input signal, which is like xi, so you might have different input signals, and then you'll have corresponding weight values. So you're just multiplying the input signal with the weights and then taking the sum. So that will be your activation value or the output. And then usually what you do is you pass this activation value to some activation function. So for example, sigmoid, and we'll cover this like what activation function is. So for example, if it's a sigmoid, that's the equation for sigmoid. and you feed in this ng here, and that will be your output, which is passed to like the next neuron. Okay. Now, this is not like something recent or something new. The first perceptron, it was proposed in, I think, 1957, and the actual hardware was built in 1960. So I will show you a picture of that. So we call that a linear classifier, where we just have a weight of vectors and a bias B. So these are the inputs, and we'll do some processing on these inputs and generate the output, which will be a binary. So in the center of the cell, we will have these weights. These weights will be multiplied by each of these corresponding inputs, and then we'll add this bias to these weights. Okay, so now the output will be 0 if the value is less than 0, or if the value is negative. So 0 is our threshold in this particular case. And if the value is greater than 0, the output will be 1. And this you would have figured out, like this is a dot product between these two vectors. Again, this we covered in the review of linear algebra. So you do element-wise multiplication, and you can represent this as a vector dot product, or you can also call that a matrix multiplication if you like extend the dimensions of these two vectors. Okay, now let's try to use this for classification of images. So let's say we have a input image of size 28 cross 28. Now we are not going to extract any features. We are directly using the pixel values in this particular case. So you have 28 cross 28 gray level image. So total number of pixels will be 786, and you can create a matrix which will be 1 cross 786. So this is like your input. Now you need weights for these. So for each pixel, you will need a weight, and therefore your weight matrix will be 784 cross 1, or you can also say that you will have a vector of dimension 784. And you need a scalar bias per perceptron, which will be like added to the value which you will get after doing a dot product between these two. So the result will be this. You have this matrix multiplication here, or a dot product, and then you will add this bias term. So this is your first matrix, your input x. Then that's your weight values. Coming from here, you can do a multiplication that will give you just one number, and matrix size will be 1 cross 1. You can add the bias to this. So this is like a simple perceptron which you can do, which you can use for image classification. So in this case, you're classifying a 28 cross 28 image. Okay. So there is a question from Yubo. Does it matter to make the input image column vector or row vector? Input image. So effectively, at this time, I will say no, but later you will see that if you have to optimize this process, then you don't like process one image at a time. You process multiple images at a time, and in that case, I think if you make these images rows, it's like more efficient. But of course, you can make them columns as well. But then you'll have to interchange like this multiplication. You'll have to bring the weights first and the inputs to the second position. But right now, I think it doesn't matter. Okay, so now, so that was just single perceptron, only one cell. Now what you can do is you can have more perceptrons, and you will need that if you have a multi-class problem. So for binary classification, you only have to predict one value, whether that object is present or not. But if it's a multi-class, then you need multiple predictions, where each of the prediction will indicate whether that particular class is present or not. So you tie like each object to each prediction. So you can simply add more perceptrons. So this is your input feature vector. And in this case, you have 3 different perceptrons. It means like you are solving a 3-way classifier. So you have 3 predictions. Okay. And again, so you can observe here that each input is connected to like all the perceptrons here or all the neurons. Now let's try to do a multi-class classification of an image. Again, we have the same image, which is 28 cross 28. So that's your matrix. Now you need a weight matrix for each perceptron. And in this case, you have like 10 different predictions. So for each prediction, you will need like 784 weights. So for 10 predictions, you are going to have 784 cross 10 different weights. Okay. And if you have an additional bias term, you can add that as well. So the resultant will be same. It's just multiplication of these two. You will add the bias. So the multiplication will be something like this. This is the first matrix, which is your input feature vector. Then these are like the weights. And then you can add the bias. Okay. So this is going to give you, you can do the math here. This is going to give you like a column vector of 10 values, and you will add like biases to each of those values. So you can have different biases for each perceptron, or you can have the same bias for different perceptron. Usually we have different biases. So you'll have 10 values of these biases, so which will get added to like each of those predictions. Okay. Now you are going to do like this extra addition, which is kind of, it's fine. It's just one more addition, but let's see like if we can get rid of that. And there is a simple way to do that. What we can do is we can add like a fake feature. So if this is our perceptron, what we can do is we can add a weight value to our weights for just for the bias. Okay, so you have 3 different weights for these 3 different inputs. So you have additional weight here, which is corresponding to your bias. And what you can do is in the input, you can just put this value 1. So what will happen is this bias will get multiplied to this value 1, and eventually it will be added to like the dot product of this x vector and this w vector. So essentially it's the same operation, but it's more convenient. Now you don't have like that extra addition. It's just dot product of 2 different vectors. And again, you can, it doesn't have to be 1 here, it could be anything. So if it's like 2, then that value will be adjusted when you learn this bias B. So it doesn't matter whether it's 1 or something else. Okay. Now your equation is simplified now. You just do this dot product and you just check the value. If it's less than 0, you will put a 0. If it's greater than 0, you will put a 1. So you don't need that extra bias addition anymore. Okay. So now that was just like one perceptron or maybe multiple perceptrons, and if you have multiple labels. But what we can do is we can have like composition of these perceptrons. Now the way to do that is to add like more perceptrons on top of the first one, and we call these layers in our multi-layer perceptron. All right, so this is like the input image or the input features. And these are like our neurons in the first layer. So in this case, we have 3. And this is our second layer. And in this case, we have 4 perceptrons. So what essentially will happen is whatever output you are generating at this particular layer, so that will be treated as input for the second layer. So whatever operation you were doing here, they will apply for this case as well. They're not going to change. Okay. And the idea is like we want to represent more complex functions, not just like a single level of transformation. And this, as I said, like you will have the inputs will be like the output of the previous layer. And these are like the things which define network architecture for a multi-layer perceptron. And the parameters are like how many such layers you have. So in this case, we have 2 layers, and then we have 1 output layer, and then we have 3 perceptrons in the first layer, 4 perceptron in the second layer, and then it's a binary classifier. Therefore, we have just 1 perceptron in the output layer. So these parameters define like the full network. You don't need anything extra. Okay. So yeah, that's layer 1, that's layer 2. Now this these inputs can be, so right now we have seen like we are just feeding in one input, but what we can do is we can feed in like multiple inputs at the same time. And earlier we had just one row in that matrix. So if you have multiple inputs, you will have multiple rows, and still that matrix multiplication will hold. And that's what I was trying to explain earlier, that you need to do the that transpose, whether the input will be a row or a column. You'll have to make sure that the operation is like consistent what you want to achieve. Okay, so you can have multiple inputs, and then each row of that matrix will be one of the input. Then this is your hidden layer 1, this is your hidden layer 2, and all of these can be represented in form of matrices. Okay, and matrix. And earlier you saw like that. What you have to do to get the output of this particular layer, just have to do matrix multiplication between these two. And to get the output from this particular layer, you'll have to do matrix multiplication between like the output of this and the weights you have in this particular layer. So essentially in an MLP, all you have is just matrix multiplication. And in GPUs, like we have special fast operations which can perform this. And that's why we do this in matrix formulation and not write like for loops for each of the neurons or each for the input image. So before we move on, a pop quiz for you. So you have, I think, like 30 seconds. If you want to answer, you can put your answer on the chat. And let's see if you can get like one right answer. Till now, we don't have, I think, yeah, we don't have a correct answer yet. Okay, you can take 30 more seconds. Still, we don't have a right answer. We have one right answer. Okay. Probably I didn't explain it well. I wasn't expecting that many wrong answers. Okay, anyways, so I think we had just 2 right answers. And we will have around 15,000. I think none of them were right. Let me see. So yeah, this one is right. Yeah, these seems like some random numbers. What's happening? Yeah, only one of the answer is correct. And I think that's the second attempt. Okay. So the right answer is 15,200. So your input feature has like 50 values, right? And in the second layer, you have 100 neurons. So for each neuron, you will have to do a weighted average of all the input values and then have one additional bias. So that means like for each neuron, you will need 51 weights, right? So for 100 neurons, you will need like 5100 weights. That's the first term here. And let's consider like the second layer, because it's a 100 class classifier. Again, for each prediction in the final layer, that prediction will be a weighted average of all these 100 neurons, right? And then there will be additional bias. So for each neuron, you have 101 weights. So that's 100 plus 1. And then for 100 neurons, you just multiply that with 100. Okay. So, okay, so there is a question from Thomas. How do we know how many biases will be used? So for each perceptron, you will have one bias, right? So okay, so that's fine. Now let's see like what's the issue with the neural network which we have seen so far. So what we have done is we have seen that we can form chains of these layers of perceptrons, and what will happen is they will be just like combination like this. So if X is your input and then H will be your function which represents the first layer, because it's just a linear combination. So Hx is like linear combination of the input. And if you pass that input to the next layer, then that will be like a linear combination again using the second layer, and then you get the output. Now this function or chain of function, you can easily flatten and reduce that to just one function. So what's essentially is happening is, even if you have like multiple layers or chain of these functions, you can represent all that chain just using one function. So there is no point in like having that many layers. It's just like you're adding more and more parameters, but essentially it's like just linear combination. Okay, so let's try to understand that. Let's do some math here. So if this is your network architecture, and let's say you have two different layers. Okay, so then the output from the first layer will be your weight matrix multiplied by the input, and then you will add the bias term. All right, so this we have already seen. Now let's say we have another layer, in this case this one. So then again you can multiply this with the output of this and add the bias term. That will give you the output. Now if you try to simplify this, so that's your Z2. Then if you replace the actual value of Z1, which is like W1 times X plus B over here, and expand this, this is essentially like multiplying two weight matrices, and this is W2B and B. All right, so that's like simple calculation. And when you multiply two matrices, that will again give you another matrix. Okay, because these are just weights, so again these will be weights. And then this operation, you can actually sum up these values. So again, you can represent that as just one weight matrix. No, sorry. So these are just weights. You can multiply that with the biases, because biases are also learned. Okay, so they are also weights. Now you can combine these two to form another bias B, and this is like coming from a first term. So this is like the initial formulation which you started with. So even if you are like adding multiple layers, you're not changing anything. It's still like a linear combination. Okay, so it will always be a linear function. Now, the other issue is what happens is if you have a linear function, if you change like something in your input, that change might reflect back in your output, and it might cause like a large change depending upon like what kind of linear function you have. So because it's like linearly, it could be like just linear scaling, right? So if your function is scaling, let's say with 100, and if you change input value by a small margin, that scaling will be easily reflected in your output. So that's a drawback of your linear function. And another issue is like the activation function in this perceptron, it's a Heaviside function. So Heaviside is like nothing but just a step function. So to cross that threshold, it's like whether greater than 0 or less than 0. So that step function is not good. You need like some kind of smoothness there to transition from negative to positive class. So what we want is, if you want like make small changes to the weights or small changes to the input, you should have like a very small change in your output. So what we can do is we can introduce some kind of non-linearity into our MLPs, and a way to do that is to like introduce activation functions. So if this is your output from any of the layer, you put this activation function, and this is like you can have different kind of activation functions. So the most popular one is sigmoid function. So what it does is whatever input it receives, it will scale it down between 0 and 1. Okay, so if the value is 0, then it will give you 0.5. So look here, like look carefully what's happening. If you increase the value gradually, so it's increasing, that's fine. But beyond a point, like after 4, it doesn't care. It's kind of saturated. So if you have a value like beyond 4 or 5, you will not see like a big change in your output from a sigmoid function. And that's like true for even for the negative range here. And the equation for sigmoid function is something like this. So you have a negative exponent in the bottom, which is added up with 1. And this has very nice properties, like it's easily differentiable and all that. We will discuss all those later on when we are talking about how we can train our networks. Now, there can be like other activation functions as well. So the way activation functions work is you will have these inputs. You will multiply these inputs with the weights. Then you're going to sum up those. You will get the output. And at this location, you're going to apply the activation function, which will change the output you have here. So sigmoid is one, which we just discussed. Then we have tanh. It's like almost similar to sigmoid, but instead of scaling between 0 and 1, it scales between -1 and 1. And so depending upon, sometimes like depending on what kind of problem you're trying to solve, you will also choose like which activation function to use. And then we have ReLU. It's kind of like widely used in computer vision. So in this case, if the value is greater than 0, you won't change it. And if it's negative, you will make it 0. Okay. Now, so some properties of this perceptron model. So it's well grounded in theory. You can see like this theorem in this book by Ian Goodfellow, that deep learning book. And then a perceptron can also like represent a NAND circuit. And as you all might know that using a NAND circuit, you can like construct any function you want. And another nice property is like if you have enough parameters, then it can approximate like any function, literally any function, by just using one layer of your perceptron. So this is really impressive. Now, yeah, as I said, like this is the image of the first like perceptron, the hardware build. So this was called Mark I perceptron. It was built in 1960. So what it did, it had like a camera which can capture at a resolution of 20 cross 20. So this was back in 1960s, and I think this was a big deal back then. So it has only 400 pixels. And these are like showing different connections or different weight values between different neurons here. And I think there they have like some hardware, I don't know exactly what, but these are like they used to simulate like the weights you have in your network. And there is a nice article about this on Wikipedia if you're interested. Okay, now the big question is, if single layer can learn any function given enough parameters, so why do we need to have like multiple layers? And that's really, that's a good question. And so the answer to that is, if you have multiple layers, then what you can do is you can do composition of different functions, and some of those functions might get reused. So by reuse means, let's say you have some function in your initial layers, and if you need that function multiple times while you do the processing. So once you have that, you can reuse that later in your network, because at some stage output from that function or whatever output that function produced, it's going to be fed into like some of the function later on. So that reusability, it's like, it makes the network more efficient, and it not only reduces like the number of parameters, it also like helps you in achieving better performance. Now, so yeah, because of this reuse, the deep networks are like better than your just single level perceptron. And if you have to implement something in single layer, then you will need like lots of parameters. So to avoid that as well, you can develop like a deep network with fewer networks or fewer neurons in each layer. So that will increase like the composition power of your network. And that's why we have multi-layer perceptrons, which is called like fully connected layer, connected network as well. And we have nonlinear activations. So this is like a simple example, which is a 2-layer MLP. We also call these like feed-forward neural networks. All right, so yeah, the goals are like simple. We want to represent complex functions which are suited for like the problem which we're trying to solve. And this means that we assume whatever data we have like in our current training set. So there is a underlying generating function which we want to mimic using this MLP. Okay, so we should be able to do that composition using these sequence of layers. And then we should be able to learn like a good feature representation, which is specific to the data set or the problem which we're trying to solve. Now, let me show you some results like on one of the data set. This is called MNIST, and this is a data set of handwritten digits. So these are some of the samples from this data set. I think we have around 60,000 training samples, 10,000 training samples. So I think a paper in 2010, they developed a MLP which has around 6 layers. Okay. So, and in each layer, they have these many neurons. So starting from 2500, 2000, 15,000, and so on and so forth. So the last layer has 10 neurons because we have 10 digits. So it was a 10-way classifier. So they showed that they can achieve a performance of 99.65%. And this is just using MLP. Now, if you do the math here, if you have 10,000 samples, so you are wrong for only 35 samples. And rest like 99,965 samples, you are predicting correctly. So that's a big deal. Now, if a MLP can do that, the question is why we need convolutional neural networks. So neural network, you know that it's fully connected layer. So let me give you like one motivation why we need CNNs, and then we will cover CNNs in the next lecture. So the input to these MLPs can be like handcrafted features, okay, like we discussed earlier, or these could be like directly the pixel values of the image. So if these are handcrafted features, then there are like many limitations of these handcrafted features because we need like expert domain knowledge to extract such features, and it's very difficult to like generalize them across different problem domains. Now, if we use image as input, then let's consider like what will be the size of the input layer. So let's say we have a small image, and so this is like just 256 cross 256 RGB image. So we'll have 3 different channels. So if we will flatten this image and transform this into a feature vector, so that feature vector will be of this dimension. So this is roughly 200K. So if you have to feed this image to this MLP, then the input layer will have that many neurons. And depending upon like how many neurons you have in your first layer, you can multiply that with this number. So that will be like your weights in the first layer itself. And that's a lot. So the point is, you can't use MLPs directly on the image pixel values because it's not scalable. And if we want to use handcrafted features, then we do have lots of limitations there. And that's why we need CNNs, and why they are different from neural network. Because what they do is, instead of like flattening the input image, they operate on like a subsection of that image, and essentially they are like operating on volume of data instead of like these flattened neurons. And there is some kind of weight sharing, and all of this we are going to cover in the next lecture. So don't worry if you have any doubt or any question here. So this operation like from volume to volume is efficient, and this weight sharing make that like even more efficient. So yeah, that's it for neural network. Any questions you have? So there is a question from Sunil. He's asking, volume, is it refers to subsection of image? So by volume, I mean, so in this MLP, right, this feed-forward network, you have these flattened feature vectors, which like get transformed from one layer to another, right? These are just flattened feature vectors. But in CNNs, we don't have these flattened features. We have volumes. So by volume, I mean they will have some width, they will have some height, and then they will have some depth. So in a CNN, instead of transforming your flattened feature from one layer to other, what you will do is you will transform your volume of features. So this is a volume, you will perform some kind of transformation here, and then you will get another volume. So by volume, I mean like a cuboid kind of structure. Okay, so if there is no other question, we can end it here. Thank you very much. Bye.